So let we wait for a couple of minutes more and then we will start. Thank you. We are waiting a bit till 2 p.m. Central European time and people are joining. So let we wait for 1-2 minutes more and then we will start on time. So I think now we can start, and I would like to start today's YAPSE webinar as moderator, as chair of Task Group 5.6, BIM Infrastructure Management, which acts within IAPSE Commission 5, which is about existing structures. Before we start, I would like to say some words about IAPSE organization, which hosts today's webinar. You know IAPSE probably very well. It represents a scientific and technical association comprising members in 100 countries and counting 58 national groups worldwide. As a non-profit organization, it was founded in 1929. It has seats in Zurich, in Switzerland. What does IAPSE deal with? Generally, with all aspects of structural engineering, where the term structures includes bridges, buildings, and also all types of civil engineering structures composed of any structural material. It deals with science and art of planning, with design, construction, with operation, monitoring, and inspection. Of course, maintenance, rehabilitation, and preservation, especially important in last days and years. Unfortunately, also demolition and dismantling of structures, taking into consideration technical, economical, environmental, aesthetic, and social aspects. Now, at this stage, I would like to invite you to join the IAPSE Symposium in Tokyo, which will be held between 18 and 21st of May this year. Our task group is hosting also special session, existing bridges and extension of BIM to bridge management systems. And chair of the session will be Professor Shim, who is our presenter today. The next IAPSE Congress in Ghent will be held between 27th and 29th of August this year. So very welcome to meet you there as well. And you can see on the web, on the page here on the slide, you can also see the invitation to the IAPSE symposium in 1 year, which will be held in Copenhagen 2026, and special topics bridging advanced technologies and structural innovation. Now, before we start, I would like to introduce you with our task group. Our task group aims to connect bridge management systems. It acts under a Commission 5, which is, here you see existing structures, but our task group has a certain aim and vision to include 3, 4, 5, 6D software and hardware independent data exchange between different software technologies during life cycle and beyond, and considering also monitoring sensor equipment and damages on the structure along time axis. Now, members of our task groups are experts from all over the world, but due to interesting content, we are cordially inviting new members who are eager to join our active task group, and you can send your interest to IAPSE headquarters, which will pass the request to me. Before starting this presentation by Professor Shim, I would like to add two information only. Please use the question and answer button for passing your questions, not the chat button below. And all the questions will be answered at the end of the webinar. Now, the webinar will also be recorded, of course, so it will be possible to rehear, share the webinar later as well. Now, let me introduce the presenter, Dr. Chang-Soo Shim. He is a professor at Chungan University in Seoul, Korea, specializing in structural engineering with a focus of BIM, digital twin technology, and three-dimensional concrete printing for bridge construction. He served as the president of KIBIM, which means Korean Institute for BIM, and is currently the vice president of Korean Society of Civil Engineers and Korean Institute of Bridge and Structural Engineers. He has published more than 90 journal papers, 15 books, and numerous conference papers, and we are very proud having him as vice chair of our task group since very beginning of 2020. So the title of today's webinar will be interesting: BIM for bridge maintenance and operation in Korea. We know that bridges represent a vital but also extremely vulnerable part of transportation infrastructures. So BIM has been mostly utilized for design and construction in the past 20 years. And the operation maintenance phase is currently just partially involved in BIM processes. So I'm inviting now Dr. Shim to talk about innovative digital technologies that improve bridge maintenance, efficiency, and reliability for both new and existing bridges in Korea. So please, the stage is yours, Professor Shim.
Thank you, Vanya, for your kind introduction. Hello, everyone. Welcome to this IAPSE webinar. Today, I will explain the application of building information modeling in the context of bridge maintenance. As you know, the BIM is widely adopted in design and construction, but its adoption in maintenance phase is not so well common situation now, and we have lots of challenges to link BIM data to the current existing BMS system or the bridge maintenance practices. As you know, the bridge ages and maintenance costs grow. There is a critical need for smarter and data-driven solutions. BIM for maintenance addresses this by linking digital models to real-time condition data, creating what is often called digital twin of the bridge. So this presentation is organized by YAPS Task Group 5.6, as already Vanya introduced. So our group has a clear mission to link BIM data to bridge maintenance system, especially using open BIM standard like IFC. And we have 5 groups. As you see in this slide, first group is on object data and data management, visualization, and maintenance and repair. And finally, user interface. We aim to make BIM a practical tool for the lifecycle management of existing structures. So let me briefly introduce the contents of today's webinar. First, I will share some BIM practices and data delivery strategies in Korea, especially, focusing on how BIM is currently used across the bridge lifecycle. Next, we will look at BIM-based bridge management system in Korea, showcasing how BIM is being integrated into bridge maintenance processes. Finally, I will discuss BIM data for operation and maintenance. This includes key components like our task group's 5 missions, object data and data management, and damage and repair data will be used to track condition and planned interventions during the maintenance period. And finally, data for key performance indicators. This will support maintenance decision-making and lifecycle evaluation. Together, these topics will illustrate how BIM is evolving from design tool into a powerful platform for long-term bridge maintenance. As you know, we have different level of BIM. BIM practices are evolving from simple 3D modeling to a more integrated form of collaboration. We often refer to this progression as a level 2 BIM and level 3 BIM. Level 2 BIM is about model-driven collaboration. We are working together based on shared 3D models. But the level 3 BIM advances this into data-driven collaboration, where structured information flows seamlessly across platforms and project participants. With the rapid growth of IT solutions like sensors and cloud services to AI and digital twins, we need a standard data formats allow BIM to interface with these external systems. This is where open data standards become essential. Successful BIM adoption needs 3 pillars, like people, process, technology. Each of these must align to achieve meaningful digital transformation. For this, in Korea, we have a national BIM standard and guidelines. We're trying to minimize any the trial and error during the BIM implementation phase in every sectors in construction industry. Now, public clients in Korea, they are beginning to develop their own detailed BIM guidelines tailored to their product needs, ensuring more consistent and effective BIM adoption across sectors. The first thing I want to introduce is our recent efforts of BIM implementation in a national R&D program supported by the government. As you know, the recent bridge construction project, there is a growing interest in applying the concept of DFMA, Design for Manufacture and Assembly. This is to improve digital data delivery from design to construction and finally maintenance. DFMA supports shift toward the prefabrication by enabling design models to directly inform fabrication and assembly processes. And we need this data for bridge maintenance. In Korea, we are actively advancing this through a smart construction R&D program which promote digital transformation across the construction industry. And mainly, I'm doing research work on this bridge construction project. As part of this initiative, we have developed the BIM standard specifically for prefabricated bridge project, with a strong focus on data exchange protocols among project participants like designers, fabricators, and assemblers. These efforts are especially effective in projects where we have prefabricated bridge members. We need accurate and structured BIM data. And this data will play a critical role in ensuring smooth coordination from design to on-site assembly. By using this accumulated data, designer can develop much better design ideas, and we need feedback to designers. A key aspect of this BIM for maintenance is transition from project information model to asset information models. During construction, we have to collect and update data like geometry models and linked data. These data should be continuously updated by design revisions or the field modifications or inspection results. At project handover time, this information is delivered in a form of completed digital package, including the model data and linked files, open using open formats, as you see the IFC. Once the bridge enters the operation phase, the bridge maintenance system can directly import this digital handover package. It becomes the foundation of the bridge information models for maintenance. From their new data, such as inspection records, condition rating, or repair histories can be added continuously. This creates living digital twin that evolves throughout the bridge life cycle. One of the most critical processes in BIM-based maintenance is the data delivery from the project information model to asset information model, as you see in this slide. During the bridge construction, the geometry model is not rigid body. It should be updated based on fabrication and assembly error, as well as actual product data such as material test results and dimensional tolerances and field inspection findings. At the handover stage, this refined information, model geometry, attribute data, and documents is delivered in a structured format, ideally using open standards. This ensures compatibility and long-term accessibility of the accumulated data during construction project. To make this process effective, we need clear guideline. The guideline will define what data must be delivered, how it should be structured, and what level of detail is required. Without this, critical information for long-term maintenance may be lost. Equally important is determining what data is essential for maintenance decision-making, such as road ratings, material inspection data, and inspection schedules, or the repair histories. In Korea, we are currently developing a national BIM guidelines for maintenance. This will define the standard procedures, data formats, and responsibilities to ensure reliable digital handover and long-term data usability. This slide shows the overview of the BIM guidelines we are developing now for maintenance. The guideline is designed to ensure consistent and effective data delivery from construction to operation phases. And it has 4 topics. First one is information delivery plan. It defines what information must be delivered and by whom and what stage of the project lifecycle. And second one is model architecture. It specifies how beam model should be structured to support long-term maintenance tasks and interoperability with BIMS. And third one is beam data for maintenance. We outlines the essential data elements required for condition tracking, life cycle assessment, and repair planning. And last one is, of course, we need a visualization. Visualization supports visual integration of inspected results, making it easier to interpret damage locations, severity, and the progress over time. Important thing is this guideline is not developed in isolation. The guideline is based on current maintenance practices in Korea, particularly focusing on inspection method and repair history documents. This ensures practically align with how bridge maintenance is actually conducted on site. By combining structural beam data with established workflows, this guideline aims to improve decision-making and transparency and also extend the service life of existing bridges. Now, let me introduce some cases of BIM-based BMS in Korea I've done before. The first case is a pilot implementation of bridge maintenance system using BIM model and data for Cable Stayed Bridge. It's a second Jindo Bridge. For this project, we selected the existing bridge to demonstrate how BIM can be integrated into maintenance workflows. Geometry models were created using standard data templates for each bridge member, including pylons, cables, girders, and deck elements. These models were enriched with property sets and linked files. We have lots of inspection records and material specifications and structural details and drawings. In this system, BIM functions as a centralized database platforms. We have existing information and newly collected maintenance data, such as inspection results and repair history. And the data will be continuously added and updated. This pilot showed the feasibility of using BIM not only for visual representation, but also evolving data repository to support long-term bridge maintenance of complex bridge structure. The main objective of this BMS is to reduce the burden of maintenance operations, particularly by minimizing reliance on fragmented documents and 2D inspection drawings. To achieve this, the system integrates existing maintenance history data into a unified BIM environment. This serves as foundation, allowing additional data such as inspection records, damage and repair logs, and it will be continuously updated in a structured and traceable manner. At the site level, we developed a tablet-based damage recording system. Inspectors can directly input damage information on site, including photos and annotations. These field data are then transmitted wireless to the bridge maintenance system, which is hosted at the management office. At there, engineers can view, verify, and manage inspection records in real time through the integrated BIM platform. This approach not only improved data accuracy and efficiency, but also improved collaboration between field and office teams, streamlining the overall maintenance workflow. After this, we persuaded Korea Express Corporation to develop the BIM-based BMS for common bridges, common highway bridges. They have more than 10,000 bridges. To support this, we developed the automated model generation algorithm. It can digitize more than 10,000 bridges of various types with minimal manual input. model creation is a huge challenge for the transformation of existing document-based BMS to the model-based BMS. A model classification system was developed to organize elements based on inspection units, such as slabs, girders, bearings, and it enabled clear mapping of inspection data to specific members. The user interface allows inspectors and engineers to visualize damage history directly on the 3D model surface. It makes it easier to understand deterioration patterns and plan maintenance interventions. Additionally, the system supports integration with UAV scanning and ground-penetrating radar data. It allows for more detailed and automated condition assessment. In this framework, BIM serves as a central platform, not only for visualizing geometry, but also for storing, updating, and interacting with all the information required to maintain each bridge effectively. We have federated models, and it's very useful for bridge managers. In this system, visual inspection results are mapped onto 3D model with the damage visualized in span level units to reflect inspection practices. Users can selectively display specific type of damage or data attributes, and it enables targeted analysis. Condition rating are visualized using color-coded scheme. It allows quick identification of critical areas for inspectors and engineers. While the system includes the capability to link scanning data, such as UAV or GPL, directly to the model, these datasets are often large in size and difficult to manage. To address this, it's necessary to define and extract individual damage objects from the scans rather than importing raw data as is. This approach improves performance, maintains clarity, and ensures that only relevant and actionable information is stored within the BIM environment. The final system I'd like to introduce is the latest development of BIM-based bridge maintenance. At the core of effective maintenance are two key data sets: the history of damage and the relevant repair history. However, in current document-based system, it is very difficult to directly associate specific damage with its corresponding repair actions. In this new system, each damage is defined as an individual object, not just a scanned image. We have an individual damage object within the BIM model. The repair history then recorded and visualized as a temporal record linked to that same object. So the damage object actually has a data of repair history. This object-based approach allows us for a clear understanding of how damage evolves over time and how effective a particular repair method has been. As a result, it becomes possible to evaluate long-term performance of repairs and estimate the remaining service life of bridge. This data-driven maintenance system provides us a robust foundation of lifecycle evaluation and informed decision-making regarding bridge sustainability and repair planning. As you can see in this slide, damage and repair data can be accumulated in the same object and with the same location as in this slide. This is initial efforts now. It will be improved continuously. From now, I will discuss core data components targeted by our task group, drawing on insight from the BIM-based BMS cases in Korea. These include object data management frameworks, visual inspection and repair history data, and key performance indicators for maintenance decision making. You know ISO 19650? Bridge maintenance information should be structured into 3 categories: model, data, and file. This structure ensures interpretability and traceability. Importantly, the information requirements must be clearly defined by the clients. This includes specifying what data should be submitted at each stage and what needs to be accumulated throughout the bridge lifecycle. Establishing these requirements from the outset is essential for ensuring that BIM models support not just design and construction, but also effective long-term maintenance of bridges. You see, these slides present example of how the geometry model of Cape State Bridge is defined, along with the interrelationship between different model components. To support effective maintenance, it is essential to standard the geometry definitions and attribute data from the perspective of maintenance managers. This standard forms the foundation of what we define as object data. The requirements are established through the identification of BIM uses during the maintenance period, which are derived by the analyzing actual maintenance tasks, such as inspection, evaluation, repair planning, and monitoring. For existing bridges, creating this information retroactively presents a challenge since the data doesn't exist in digital forms. Normally, we have lots of documents and very simple information system. So we need efficient method to generate or import the necessary models and data from the existing information. A critical decision in this process is scope of data to be included. Should the system cover only inspection records, or should it also incorporate maintenance actions, repair histories, or even health monitoring system data? The answer depends on the intended use of BIM model in long-term bridge management. By clearly defining object data based on real maintenance needs, we can ensure that BIM becomes practical and valuable tools, not just the visualization of bridges. When a new bridge is targeted, it is essential to clearly define the content and format of information that must be submitted at the time of project completion, as we discussed before. This includes not only geometry models, but also structured attribute data and linked documents required for long-term maintenance of a bridge. To make sure smooth integration into bridge management system, the contractor must deliver the information directly to the database, following the predefined information specifications, which is defined by the clients or asset owner. By aligning information delivery with the maintenance system's data requirements from the outset, we can reduce redundant work and improve data consistency and ensure the handover model is immediately usable for operation and maintenance. BIM data requirements for maintenance system must be defined with a clear purpose to evaluate the performance of bridge structures or to support informed maintenance decision-making. Structured and standardized data will provide us a foundation for applying advanced data analysis and simulation technologies. It enables more accurate and reliable performance assessment of the bridge structures. To achieve this, it is essential to establish formalized information delivery framework, which define the required data drops at each project stage As you see here, we need very detailed information definition from design and construction to handover. By doing so, we ensure that critical data is captured systematically and remains accessible throughout the bridge life cycle. And it can be seamlessly integrated into the management system for continuous monitoring and decision support. We need also analysis model. In order to evaluate structural behavior of bridge, analysis model is essential. And this model allows us to simulate and assess the response of structure under various conditions. One effective approach is to develop the baseline model at the time of project completion, supported by the data from accumulate the data handover and also the load test. It can provide us a calibrated reference and reflect bridge's actual performance at the start of the service. While it may not be feasible for all structures, implementing this approach for major or critical bridges enable us continuous performance assessment throughout the bridge life cycle. And also the baseline model can be linked to the structural health monitoring system, and it can capture key behavior data in real time, such as displacement, stress, and vibration, improving the model's utility for predictive maintenance and safety management. The integration of analysis model, load testing, and sensing system provide us a robust framework for data-driven performance evaluation and long-term bridge reliability. As you know, currently we have this kind of a document and 2D drawing-based maintenance practices. Bridge maintenance has long relied on this periodical visual inspections, and we have a significant amount of data, primarily in the form of documents, reports, and drawings. To fully leverage this legacy data in modern maintenance system, it is essential to digitize and structure the information so it can be integrated into BMS. Given the sheer volume of historic data, we need batch conversion technologies such as automated text and drawing recognition, and it can play a critical role in accelerating this process. Once digitized, this data provide a foundation for developing a digital twin of bridge, enabling not only visualization of past and present condition, but also simulation of structural behavior and finally prediction of future performance. By combining historical inspection records with a real-time monitoring and predictive modeling, digital twin will give us powerful tool for proactive and data-driven bridge maintenance. This slide presents one example of how crack damage in a bridge slab can be extracted from traditional inspection record drawings and transformed into digital damage object. By applying standard damage classification code and structuring data such as location, type, and severity, each damage instance can be digitally represented and tracked. This allows for modeling the progression of individual damage over time, enabling maintenance teams to assess deterioration trends with a greater accuracy. Furthermore, by accumulating material test results, such as carbonation depths, chloride concentration, or rebar exposure, with the visual data, damage inspection data, we can work together toward the standard of data model for damages. This integrated approach not only improves damage assessment, but also support predictive modeling of lifecycle-based maintenance planning. We are currently developing the damage models of cracking, especially for bridge slabs. And this type damage data need to be managed in conjunction with the associated repair history, as I explained before. And it gives us comprehensive understanding of how damage evolves and how effective specific repair actions has been. To optimize both functionality and performance, it is good to separate the 3D visualization model from the underlying database used for data analysis. This separation ensures the visualization remains lightweight and responsive, while analytical processes can handle structured and scalable datasets. In addition, the hierarchical structure of the model must be carefully defined to support efficient data handling. As we see the bridge models and the member models, and also damage and repair object we have. Organizing the components and damage objects in a logical and analyzable hierarchy, such as by span, member, and damage category. It improved usability for both visual review and assessment of bridges. This dual structured approach strengthened the integration of visual inspection workflow with the data-driven maintenance strategies. Final things I want to explain is the data for key performance. DMS is developed for managers or engineers to assess the actual performance of existing structures. With the consistent data management across the entire life cycle of bridge, it becomes feasible to quantify the effect of material deterioration, damage progression, repair activities, and structural strengthening. This can open the door to validating and improving many of empirical equations currently used in our design codes, which are often based on the limited data sets or assumptions. Moreover, by analyzing data related to the design variables and in service conditions, we can perform probabilistic evaluation of structural behavior, allowing us for more accurate prediction for future performance. Sorry. We also can have the very simple monitoring system to track the real behavior of a structural member. And we'll link the data with the simulation models. In this way, we can build a platform for data-driven and performance-based bridge management. In bridge management, the primary performance criteria are safety, serviceability, and durability, as you know. More recently, service life assessment has been more and more critical because it influences long-term maintenance strategies and investment decisions. To support this, the necessary data for each limit state, such as ultimate strength, deformation, material degradation, it should be clearly defined across the design, manufacturing, and maintenance stages. These data sets are then integrated into a unified data model, forming the backbone of a comprehensive bridge maintenance system. Such data should not only be defined in a theory, but also actively collected during the current maintenance practices, including the inspection records and material test results and repair histories. Through this structured and continuous data accumulation, we can build a digital twin. Not only the bridge as a whole, but also individual material and structural members. We can do the performance tracking, predictive analysis, and life cycle optimization of our bridge. Let me share an example from our current research work. Among the structural members of bridge, the bridge slab typically has a shortest service life, making it a priority for predictive maintenance. We are now actively collecting data and developing digital twin models specifically designed to estimate the remaining service life of this bridge slab. Traditional visual inspections and condition ratings are often insufficient to accurately determine the actual service life, and bridge managers have difficulty to have clear definition of service life. What is service life? How to decide the demolition of existing bridge slab? Our approach involves modeling the time required to reach defined damage state. We have 8 states, integrating not only visual damage history, but also repair records and material deterioration data, such as chloride ingress, carbonation, and rebar corrosion. This allows the model to predict service life dynamically, taking into account key design variables like slab thickness, reinforcement detail, and environmental conditions, such as traffic load or the exposure to de-icing salt. Finally, this twin model will provide us a data-driven framework for lifecycle assessment and maintenance planning tailored to actual bridge performance. This is another example for precious concrete girders. 2 major challenges in maintenance. First one is the evaluating long-term structural behavior. And second one is detecting the internal damages like tendon corrosion, which is not directly visible. In our current research, we begin by building baseline models established through early stage monitoring of bridge girders' behavior. Using a very simple sensing system, we track key parameters such as initial deformation, pressure loss, and material properties changes over time. This monitoring data allow us to understand the structural performance during its early service life, and it will give us a foundation for future comparison with simulation models. Building on this, we are developing a digital twin model. The focus is specifically on key performance indicators, particularly those significantly influence on overall structural integrity like a tendon corrosion. Rather than simulating all aspects of behavior, the model targets critical performance elements. It can compromise safety or function, providing a focused data-driven tool for decision-making in maintenance tasks. In the context of maintenance, it's often difficult to deterministically evaluate the current performance of structure due to uncertainties in material properties, damage propagation, and environmental influence. We need a probabilistic approach, and we can assess structural performance based on the variability and uncertainty of key influencing factors. To support this, it is essential to collect and accumulate actual values of major variables, such as material properties and material degradation rates, load histories, repair histories, and environmental conditions during the real project. If the data requirements I've outlined today for beam-based maintenance system are integrated into actual bridge project, the reliability of performance evaluation can be significantly improved. Moreover, because many provisions in current design codes are not grounded on long-term field data, the accumulated empirical data allow us to propose more realistic and evidence-based revisions to our design standard. In this regard, BIM can serve as a powerful tool for collecting and structuring and storing such data across the life cycle of a bridge. And it is essential to establish standard data protocols and promote collaborative research among designers, contractors, and maintenance authorities. Okay, this is the conclusion. Today, I presented ongoing efforts by our committee to promote the use of BIM for existing structures with a focus on improving bridge maintenance and life cycle management. While this research is still in its early stage, it holds significant potential and achieving meaningful results, and it will require sustained time, efforts, and collaboration with us. In particular, the collection and utilization of real-world maintenance data is a critical challenge that cannot be addressed by a single organization. It demands collaborative research, active field engagement, and alignment between academia, industry, and public agencies. I believe that both national initiatives and international cooperation will be essential to advance this maintenance field. I hope to see continued and expanded collaboration, especially through platforms like IAPSE, to realize the full potential of data-driven maintenance using BIM data. Thank you for your attention.
Thank you very much, Professor Shim. I think the presentation was more than impressive, really very interesting, and it is showing a great approach in Korea. So I'm very, very sure that international collaboration will be booming in the next future. We have here some questions. If I may give you the first one. Which software have you used as BIM?
Software?
Yeah.
We have multiple different kind of softwares like Autodesk Revit and Dynamo, Grasshopper, and the MicroStations. It depends on the situation. So we like to use data-driven modeling through the algorithm. We need to minimize the software locking effects. So OpenBIM standard is quite meaningful, but practically it has a limitation. So we need to solve that by the data-driven modeling process, right?
Very good answer. And here we have also the question, which is somehow good. How can the long-term data management challenge of BIM be addressed, especially considered the high cost of commercial software and issues related to data ownership for bridge owners?
Yeah, nowadays it's very important issue for any public clients, bridge owners. Data ownership is really critical, and also the cost for the commercial software during 100 years of bridge life cycle. They don't want to pay money for every year. So I introduced 3 different kind of PMS system. Those systems are wholly standalone software. We only hand over BIM data to the BMS and BMS is handled the standalone system. It's not a commercial system because it should be maintained for more than 10 years at least, right? But the commercial software always change their version. And every update of software, the clients have to pay. So that's a big challenge.
Thank you. And then we have one more. It's longer. What strategies or frameworks can be implemented to enable effective collaborations and data sharing among different breach owners, particularly for utilizing accumulated BMS data to enhance maintenance practices?
Yeah, that is also a very challenging issue because as I explained to you, we need to collect damage and the repair histories, not just from one single breach owner, from multiple breach owners, but they don't like to share the data, right? That's the problems because sometimes they have very the sensitive situation during the maintenance task. So one solution is the using federated data strategies. Federated means we can share some model or algorithm for the analytic solutions, like when we want to develop the damage models, like cracking, we want to know the influence factors for the cracking and crack propagation to reach the final service life. So if we agree to have the same model, and every breach owners can share the model, and they can train their own model by their own data, and share the parameters only. That is a federated AI methodology. So in Korea, I'm trying to persuade breach owners to agree on this strategy to develop more reliable damage models and deterioration models, and finally digital twins for existing breaches.
Thank you very much. I think we are also hard working in our task group where you are vice chair. Very actively also discussing with breach owners worldwide. What we will now also present at IAPSE Tokyo in our special session where you will be the chair. And I think that the things are moving forward. As we know, the age of bridges is critical now, 60, 70 years, a lot of collapses and so on. So I believe maintenance operation, very important part of the bridge life cycle. And I wish that really cooperation among different countries will be stronger and important in the next future. So I think if there is no other questions, I would like to thank Professor Shim. It's quite late today already in Korea, so I will need to sleep. I also like to thank all the participants who will be able then to download also and to share this live presentation in the next future. Thank you very much and all the best.
Okay, thank you.
Thank you. Bye.